Condition for continuity of a function is limit x tending to a fx must be equal to x. This is the basic condition of continuity of a function. If limit exists, sometimes we split the limit. That limit x, we write it in the form of left hand limit, then right hand limit, and functional value. If they are equal, then the function is said to be continuous at the point x equal to a, where to c. But today's class we are going to discuss discontinuity of a function. A function is said to be discontinuous at a point if any one of these two equalities not satisfied. For example, if this thing is not equal to this, or this not equal to this, or this one not equal to this one, then the function is said to be discontinuous. But there is another way to see discontinuous function. At a point, the value of the limit may be equal to infinite, or it does not exist at all. In that case, we will say that the function is discontinuous and it belongs to the second category. Okay, so let me tell you discontinuity of first kind first. Discontinuity of first kind. What is that? In this case, this is called LHL, this is RHL, and this is functional value. Okay. Now, when a function is discontinuous of first kind, then in this case, LHL, RHL and FA all exist, but the condition of continuity is not satisfied. Okay, so it means LHL not going to be equal to RHL, or this is not equal to the functional value. It's like that. But both the limit exist. I can take one example for you here. The simplest one I am starting, that if x equal to 5 plus x square when x greater than equal to 1, 7 when x less than equal to 1, sorry, x equal to 1, when you write this way, this is greater than 1, this is equal to 1, and next one 8 minus x when x less than 1. Okay, if you want to find the limit of this function at greater than 1, I mean LHL, if we write, this is going to be limit x tending to 1 minus fx. This is nothing but limit x tending to 1. This part you know. This is 8 minus 1, that is equal to 7. What about RHL, right hand limit? This is limit x tending to 1 plus fx. This is going to be equal to 8 minus 1, because we will be using this part, we will be using the first part. So limit x tending to 1, 5 plus x square, which is equal to 5 plus 1, this is equal to 6. And f1, what is the value of f1? f1 is 7. So you can see these two are equal, but they are not equal to the RHL. So the function belongs to first type of discontinuity, the discontinuity of first kind. So fx is discontinuous at x equal to 1. Let me take the second example for it. Suppose you are defining a function like fx equal to, say we are taking this manner, 2 by 1 plus e to the power 1 by x, when x not equal to 0 and this is equal to 5 for x equal to 0. How to check continuity of this function? Is it belonging to the type 1 discontinuity here? Let us see whether it belongs to type 1 discontinuity or not. We will be finding the left hand limit, the right hand limit and the functional value. Functional value is quite obvious here, that f0 is equal to 5, limit x tending to 0 minus fx. This is going to be 2 by 1 plus e to the power minus 1 by 0. It is e to the power minus infinity. E to the power minus infinity is 0. 2 by 1 plus 0, answer is 2. Okay. And the right hand limit, limit x tending to 0 plus fx. This will be 2 by 1 plus, if you put 0 here, it is going to be 1 by 0 infinity. So e to the power infinity is infinity only, that plus 1 also infinity, its value equal to 0. We need not proceed. We can see that functional value not equal to the left hand limit, not equal to the right hand limit. So this also belong to the type 1. Therefore fx is discontinuous at x equal to 0, not infinity, at x equal to 0. So both these functions are belonging to discontinuity of first kind. Okay, so all of you understand what is discontinuity of first kind. Now I am going to explain under this category, discontinuity of first kind, what is the meaning of piecewise discontinuous function. Piecewise discontinuous function. What is that piecewise discontinuous function? If a function is first kind of discontinuity, I mean not obeying the condition of discontinuity, but limit exists and number of discontinuities over an interval is finite, then the function is said to be piecewise discontinuous function. Okay, just I am writing, if a function has finite number of discontinuity of first kind, in an interval, then it is said to be piecewise discontinuous function. I just give you one example what is piecewise discontinuous function. The best example I can take here, that fx equal to the greatest integer function on -2 to 3 in this interval. Okay, I can finish it by plotting the graph very fast, so I favor plotting graph here. In -2 to 3, if we want to plot, then the graph will be like this. Okay, this point is -1, this is -1, this part is 1, 2, 3, like this. So in -2 to 3, all of you can see that at the point, say suppose we are taking x equal to 2. What is the left hand limit here? That you know very well, limit x tending to 2 minus fx. If you find its value is going to be equal to 2 minus modulo, if you calculate, this is going to be 1. and limit x tending to 2 plus fx, it is modulo 2 plus 0, it is value 2. Okay, and what is the value of f2? F2 is also 2. Okay, so you can see all three are existing over there at the point x equal to 2, but the function is not continuous because this is not equal to this. That's why. Similarly is the case for -2, -1, 1, 2 and 3. So in this interval the function is piecewise discontinuous at how many points? You will say at 5 points. So you can say that the function fx equal to modulo x is piecewise discontinuous in the interval -2 to 3. We can find another example. Suppose the function is stated this manner. Example 2 I am taking here. Suppose fx equal to 3 minus x square, x greater than equal to 1. It is x greater than equal to 1, 4 plus x, x less than 1, 2 minus x square, x greater than equal to 2, and 5 plus x, x less than. How many? Is it a piecewise discontinuous function over the interval? Say I am taking 0 to 5. Yes, here it is a piecewise discontinuous function because this function has discontinuity at the point x equal to 1 and x equal to 2. At x equal to 1, if you are going to find the left hand limit, the value of the function going to be equal to 5. Right hand limit you can see 2 and functional value is also 2. Okay. So in this case, discontinuous at 1. So it is a, therefore fx similarly at 2. At 2, what is the right hand limit? It is going to be equal to -2. Left hand limit, that is equal to 7, and functional value is also -2. So they are not equal, therefore fx is a piecewise discontinuous function. Piecewise discontinuous function in 0, 5. Over this interval, it has 2 points of discontinuity. That's why you will say that it is piecewise discontinuous function over there. Alright. Now we can go for discussing the continuity of second kind. I have told you there are 2 types of discontinuities basically we learn, that is, one is the first kind of discontinuity, the other one is discontinuity of second kind. What do you mean by discontinuity of second kind? Discontinuity of second kind. Okay. Here, in case of discontinuity of second kind, you can achieve the condition of discontinuity 2 different manners. Either limit any one of the limit, any one, left LHL or RHL, either limit doesn't exist or the value of limit at a point is infinite. Then you will get discontinuity of second kind. For example, if we take fx equal to 1 by 5 minus x, okay, and they have asked you to check continuity at x equal to 5. What will you get? At x equal to 5, let us calculate the left hand limit. Left hand limit at x equal to 5 going to be what? limit x tending to 5 minus 1 by 5 minus x. If you substitute 1 by 5 minus x, that value of left hand limit, this will give you something a positive quantity. I mean 1 by 0 plus 0 kind. So it will give you the value which is equal to plus infinity. If you find RHL at x equal to 5, what do you get? RHL means 5 plus something. So you will get limit x tending to 5 plus 1 by 5 minus x, which is nothing but 1 by minus 0 type, that is minus infinity. So x equal to 5, at x equal to 5, the function fx has second kind of discontinuity. Okay, and limit doesn't exist, that also limit is there. For this function, if they say that the function is fx equal to, I am taking this manner, that 1 by x minus 1 into x minus 2. If you take the function this way, fx equal to 1 by x minus 1 into x minus 2. What will happen? This has no one-sided for this function. Okay, at which point, at x equal to 1 and x equal to 2, it has no one-sided limit at x equal to 1 and x equal to 2. So this is said to be a discontinuity of second kind. Okay, all of you understand? So in this session, we will be discussing whether continuity can be removed or not. Discontinuity can be removed or not. Function discontinuous, what way that you know, first kind of discontinuity, second kind of discontinuity already done. Now problem arises, what to do with discontinuous function. Sometimes we need to redefine a function so that it becomes discontinuous. That is said to be the extension part of our discontinuous function, where we are going to make it continuous by changing a part of the function. Which part you guess? That part is going to be the functional value part. Here, in case of removable discontinuity, sometimes you cannot remove. Why you can't remove? If limit doesn't exist, you have nothing to do. If the limit of function doesn't exist, you have nothing to do. But if the function has limit which is finite, limit that left hand side limit equal to right hand limit, but functional value not going to be equal, or just the limiting value existing, you are not getting the functional value at a point. Try to understand what I am saying. Based on this, we will be defining missing point discontinuity and isolated point discontinuity. Okay. So in this case, in case of removable discontinuity, in this case, both LHL, that you know very well, left hand limit, and RHL exist. But either they are not, either the functional value, either the functional value is not defined, or it does not exist at all. Okay, then the function is said to have removable discontinuity. It means we can change the condition of functional value part, and then you can write we redefine the function to make it continuous. That will be continuous extension of a function when we redefine that. Okay. So based on this concept, where both LHL and RHL exist, and either the functional value exists or not. If functional value exists, it is not equal to the limiting value. In that case, the discontinuity will be of two types that we can distinguish as missing point discontinuity and isolated point discontinuity. What is a missing point discontinuity? For a missing point discontinuity, at that point, the functional value is not defined. That's why it is missed. Missing point means something is missing. Which one missing? Just let me take one example here. Let fx equal to 3 minus x 16 minus x square by 3 minus x. Okay, just function given this way. Can you see this function is missing point discontinuity? Yes, this has missing point discontinuity because the function, the way you are supposed to state, not stated. What is the functional value? Functional value not given over there. We'll say that here. So missing point discontinuity, limit x tending to a fx exists, but fa not defined. Okay, then it is missing point discontinuity. Let's see what is happening there. You calculate limit x tending to 3 minus or just x or fx, or limit x tending to 3 plus, or simply you find limit x tending to 3. Let's see whether it exists or not. Limit x tending to 3. Does it exist? Limit x tending to 3. If you find left hand limit, right hand limit, there is no difference, because in both the cases this will get cancelled. So let us find this limiting value without calculating the separate one. This is going to be limit x tending to 3. 3 minus x 16 minus x square by 3 minus x. Cancel these two. This is going to be x not equal to 3. So this is nothing but 16 minus 3 square, 16 minus 9 equal to 7. So you see here this function has a limit which is defined. Limit x tending to 3 fx exists, but what is f3 here? F3 going to be equal to 0 by 0. Okay, so this is removable discontinuity of this kind, which is known as missing point discontinuity. Now a question arises, can we remove the discontinuity here? Can we remove discontinuity here? Question is yes, we can remove, because the limit exists. That's why we'll try to remove the discontinuity by redefining the function. That redefining part I'm doing here. Here, discontinuity can be removed by redefining the function. It means the major part you are not going to disturb. Only the functional part which was not there, that will do. So here we will redefine the function this manner. Fx equal to 3 minus x 16 minus x square by 3 minus x for x not equal to 3. and this is equal to 7 for x equal to 3. Alright. So now the function is going to be a continuous function, and we will say that this is referred as continuous extension of a function. This you name as continuous extension of a function. Okay, this is called continuous extension of a function. Function was not defined at that particular point. We have defined at that point, and then we are bringing the condition for continuity of the function. It is said to be continuous. It is said to be continuous now, but initially it was in this category, missing point discontinuity. Okay. So you all understand, missing point discontinuity will solve many problems afterwards. But let me do one thing first, that removable discontinuity of second kind, that is called isolated point discontinuity. What happens in isolated point discontinuity? Let's see. This is isolated point discontinuity. What is that? Isolated point discontinuity. Here, in isolated point discontinuity, just let me give you one example first. That fx going to be x cube minus 27 by x minus 3, x not equal to 3. Okay, and then it is given 10 for x equal to 3. Isolated point. At that particular point, the functional value will be isolated. Isolated from where? It will be isolated from the limiting value. Then you will say that there is isolated point discontinuity. Function is there, limit exists, but that limiting value not going to be equal to the functional value here. So isolated point discontinuity you can define here. Here limit x tending to a fx not equal to fa. See the difference between the that missing point discontinuity and isolated point discontinuity. Missing point discontinuity, fa was not given. In isolated point discontinuity, fa is given, but it is not equal to the functional value. But this kind of discontinuity also can be removed by redefining the function. So continuous extension is also possible here. Let's see what is happening there. If we find limit extending to 3 fx, what do you get? Limit x tending to 3 fx will be limit x tending to 3 x cube minus 27 by x minus 3, that is limit x tending to 3 x minus 3 x square plus this is 3x plus 9, that divided by x minus 3. Since x not equal to 3, it is tending to 3, so we'll write its value as 3 square 9 plus 9, which is equal to 27. Okay. So limit extending to 3 fx exists, but this is not equal to 10. So the function, we will say that it is discontinuous at x equal to 3. What is continuous extension here? Let's see. If you want to make it continuous, continuous extension of the function is as follows. It means you need to redefine x cube minus 27 by x minus 3, x not equal to 3, don't write 10 over there, you just write equal to 27 for x equal to 3. Discontinuity is removed, that's why I told you it is removable discontinuity. Okay, it is isolated point discontinuity and it is removable. Previous one was missing point discontinuity, that was also removable. Everyone, end of discontinuity topic which we have started discussing. before, can you remove discontinuity always? Obviously, answer is no. If a function has limits, they are equal, then only you can remove the discontinuity. But if limit existing, they are not equal, then you can't help. We cannot remove discontinuity over there. There may be functions which is oscillating above the point. We cannot remove discontinuity. Okay. So if there is a removable discontinuity in our discussion, irremovable discontinuity already will enter, and there will be no continuous extension of function in case of irremovable discontinuity. What is happening there in irremovable discontinuity? Let me explain one by one. First, I explain that infinite discontinuity. What do you mean by infinite discontinuity? It's quite obvious from the definition only. A function is said to have infinite discontinuity at a point. Function said to have infinite discontinuity at a point if the limiting value is, if value of one-sided limit, you better write this manner, value of one-sided limit is infinite. Okay, then it is said to have infinite discontinuity. For example, let us take the function fx equal to x plus 2 by 3 minus x. What will happen there if you find the limit at 3, the left hand limit x tending to 3 minus fx going to be what? That is 3, 2, and this is 0. So this is going to be plus. Similarly, if you find limit x tending to 3 plus fx, what will you get? This is going to be 3 plus 2 by 3 minus 3. 3 minus 3 plus. So you will not get plus 0 over there. You will get minus 0. So it means minus infinity. So what is happening there? The two limits, if one of them is infinity, then also we will say that there's infinite. Here both going to be equal to either infinity or minus infinity. Then this kind of function is said to have infinite discontinuity, and in this case we cannot remove the discontinuity of the function. Okay. Now let us see another example. This is problem 1. Problem 2, let me explain, where we will write fx equal to, say there is 3 to the power 10x. Does it have infinite discontinuity? Yes, it has infinite discontinuity. If at which point? At pi by 2. If you want to find limit x tending to pi by 2 plus, what its value going to be? This is going to be just tan x function is, if you don't mind, pi by 2 plus. What will happen there? This point is pi by 2. This is 0. Pi by 2 plus means this is going to be minus infinity. What is the value of 3 to the power minus infinity? 1 by 3 to the power infinity, that is 0. And limit extending to pi by 2 plus what? That is 3 to the power tan infinity, pi by 2 plus. Sorry, pi by 2 minus. Pi by 2 plus we found. Pi by 2 minus, if you find just before it, it is going to be 3 to the power infinity, which is nothing but infinity. So this also said to have infinite discontinuity. If one of the limit, any one of the limit or both the limit has value infinity, then we will say that it has infinite discontinuity and we are unable to remove discontinuity from there. Let me take another example of infinite discontinuity. This is a very common example, probably the diagram I am taking here, which is based on that. Oh no, this is the this function you can say it is of the form fx equal to 1 by x minus. It's a nice, no problem. This point also has infinite discontinuity. This is the point A. If you want to find limit x tending to a minus fx, this is going to be 1 by plus 0, that is infinity, and limit x tending to a plus fx, this is going to be minus infinity. Quite obvious from the graph also. Alright. Now I want to take another example here. Say fx equal to 1 by x square. This function graph also you can plot nicely, easily. The graph of the function is like this. If you are going to the point 0 from LHL or left hand side or from right hand side, both are giving plus infinity. So it is said to be of infinite discontinuous function. It belongs to that category. Okay. In this context, let me explain what is pole discontinuity. What is a pole discontinuity? You just consider what is pole of a function. Just let me take one example. Fx equal to 1 by x minus 3 into x minus 4. What is the pole of this function? It has two poles, x equal to 3 and x equal to 4. It is better to say a function y equal to fx, y equal to fx is said to have a pole at x equal to a if limit x tending to a 1 by fx equal to 0. Okay, this has two poles. It has two poles. If you put 1 by fx equal to 0, here poles are given by poles are x equal to 3 and x equal to 4. These are two poles. Okay, this function has pole discontinuity or infinite discontinuity. But the function, if we define this manner, fx equal to say log x ac, and we are taking it for x greater than 0, and this is equal to x square for x less than equal to 0. This doesn't have a pole discontinuity. It does not have a pole discontinuity. Why? Because of the definition from here. 1 by fx equal to 0. Here 1 by x square will never be equal to 0. 1 by log x will never be equal to 0. So pole discontinuity always will come under discontinuity, which is infinite discontinuity. From limit point of view, the value will be infinite here if you want to calculate limit extending to 3 fx or limit extending to 4 fx. Okay. So this is irremovable discontinuity. We cannot get continuous extension of function here. So this type is discussion is done. Now we will be solving problems later. Let us know what is jump discontinuity. Jump discontinuity is a very interesting problem in mathematics because they ask you to calculate jump of a function. What is that? Jump of a function. Just let me take one example. Not exactly this function I am trying to take. Okay. Let y equal to 5 minus x. This is for x less than equal to 1, and this is equal to say going to be this. If you take parabola and define the function that manner, that is say y equal to 4 plus x square when x greater than 1. It's not exactly that. Imagine that. Okay. So y equal to 4 plus x square. This one is said to have jump distance. Why? Because if you want to find limit x tending to 1 plus, we are discussing jump discontinuity. I'll define it. Let me find the jump. And what is jump? Let me explain. Then I'll define the function. Their limit extending to 1 minus fx is what? All of you know is this part of the function, that is 4. And limit x tending to 1 plus fx is what? This is going to be 4 plus 1, that is equal to 5. Okay? So this function has a jump. This function graph is not this. This is just taken for example. You plot the graph, it will be above x-axis only. Just rough estimate I can give you, not required now. So, okay, let me draw it. As I have started this, y equal to x square plus 4. This will be or x square equal to y minus 4. When x equal to 0, y is going to be 4. So it will be like this. But you cannot take from here. We are taking it from there. And this is the function. Okay? Wait a minute. Rough sketch of the function I am doing here. This is the point x equal to 1. At this point it has jump. What is the jump here? Jump of this discontinuous function is equal to limit extending to 1 fx minus limit extending to 1 plus fx minus limit extending to 1 minus fx. That is 5 minus 2. This is equal to 1. Okay. Now we can go for formal definition of jump discontinuity or finite discontinuity. This is better say finite discontinuity first. We define, then we'll see. Actually both are synonyms, jump and finite. So a function y equal to fx is said to have jump discontinuity at x equal to a if limit extending to a minus fx not equal to limit extending to a plus fx. People can say that this is a minus and this is a plus. You can state. And what is the value of jump? Jump is going to be a plus minus a minus. We define this. Very easy to calculate. Jump discontinuity you find in case of any function and you calculate. Let me explain the third kind of, and here also you can never remove the discontinuity. Continuous extension is not possible. Continuous extension of fx is not possible. Alright? Then you go for oscillating discontinuity. The third kind of irremovable discontinuity. The graph of function is quite obvious here. At this point x equal to a, it is oscillating. Better I take the example of sine 1 by x graph. This fx equal to sine 1 by x graph. I am trying to plot, it will not be very accurate. Oh, not. These are very close. Not perfect one. Better use GeoGebra to do it later. Right now you just assume that graph plot for sine 1 by x. This time the function is not continuous. Because at it not continuous at which point? at x equal to 0. At x equal to 0, value is oscillating. It oscillates between minus 1 and plus 1. You can't predict which one going to be the value of it. This is said to be the third type of irremovable discontinuity, which is known as oscillatory discontinuity. Oscillatory discontinuity. You can write the formal definition of oscillatory discontinuity. A function y equal to fx is said to have oscillatory discontinuity at x equal to a if at least one-sided limit does not exist because of too much oscillation of the function.